Uh, Hello, everyone. So this is going to be the videos that I will record where I'm solving problems for that will be useful for your exam. So what I've done is basically I have chosen several problems from the practice sheets that I gave you, and also a few from the homeworks. So I will record first some related rates problems. I will solve them and show you step by step how I do them. And after that, I think I might just, like split this. Well, just do a video on related rates and then do another one on some other kind of problems and then another one about implicit differentiation. And then I will do, I think, a last one on the homework, like the problems that I got from your homework assignments. Okay, that's what I have planned to do. All right, so let's then start with related rates. I chose problems 52, 62, and 64 from the practice sheet that I gave you guys. Remember that related rates, it's section 3.6, I think. Yeah, it's a section on implicit differentiation and related rates. Okay, so I'll start sharing my screen. OneNote. There you go. Okay, so this is the first related rate problem that we'll see, 52. So here we have a car leaving an intersection traveling east. Okay, so what I've done here is I have drawn the intersection here, and the car mentioned in the first sentence is this one over here. Okay, this one over here. So it's the car leaving east, and it says that its position t seconds later is given by this function x equals t squared plus t feet. Okay, so this function tells you the position of this car. So let's go ahead and write it here. Okay, so x equals t squared plus t. Okay, so this function tells you the position at any time t that you decide to plug in, right? Well, you see already then that it's a function of t. It depends on t, right? So let's go ahead and instead of calling it just x, let's call it x of t, right? Because it's a function of t. Okay, so that's for that car. At the same time, another car leaves the same intersection heading north. So that's this car over here. And traveling y equals t squared plus 3t feet in t seconds. So this is the function that tells you the position of this other car for any second t that you choose. All right, so let's then write it down over here. But as you can see, in the same way as x, y is also a function of t, right? So we can write this as y of t equals t squared plus 3t. Okay, so we have these two functions, x and y, that tell us the position of these two cars. Now the question says, find the rate at which the distance between the two cars will be changing 5 seconds later. Okay, so the key thing that we should notice in that last sentence is find the rate at which the distance between the two cars will be changing. The rate at which the distance between the two cars. Okay, so, and this is, I want to highlight because remember that, well, the way I have been, or we have been solving these kind of problems, we begin by writing down the measures that are being considered in the problem, right? So right now, what we have written here, we already have written down two measures, right? So we have written down, so let's actually go ahead and write down our measures. So measures that are being used in the problem. So we have x of t, right? Which is the position of the car heading east. So t squared plus 2 plus t. We have y of t, which is the position of the car heading north, t squared plus 3t. And then there is that last measure that we must take into account because of what what is being said in the final sentence there in the problem. Find the rate at which the distance between the two cars will be changing 5 seconds later. So it looks like the distance between the two cars is another measure, right? That we should consider. So the distance between the two cars is going to change with time, right? So it's also going to be a function of time, right? So we need to come up with a label for it, like, this is a function that we need to consider. So let's go ahead and call it z of t. Okay. We don't know what is equal to. I mean, we can figure out what is going to be, and of course, it's going to depend on x and y. And I guess you could already see that it's going to be it's going to come from the Pythagorean theorem, right? Because we have this leg over here is given, the length of it is given by y of t. This other leg, this other length is given by x of t, and the distance here, the shape that is being formed, or the shape that is kept the whole time, is that of the right triangle, right? So this hypotenuse is the distance between the two cars, right? So we know that z of t is going to come from the Pythagorean theorem, right? Using x of t and y of t. But we don't need to worry about, writing out the function for z of t. Okay? You can go ahead and do that, and you should get the answer. But I'm not going to do it that way. Okay, because it involves taking a square root of some super big expression. So I'm not going to bother with that. I don't need to. Okay, so this is another measure that I need to take into account, the distance between the two cars, which I'm calling z of t, and I'm just going to write down here what it means. Okay, so distance between the two cars. Okay, all right, so that's the measure. Now, okay, so that is one important thing that you want to write down when you are solving a related rates problem. Okay, the measures. Okay, now there is another big step that you need to make, is that of writing down the equation that relates your measures. So equation that relates your measures. Okay, so as we have said before, that equation is going to be the one given, well, it's going to come from the Pythagorean theorem, right? Because we have that right triangle. Okay, so but let's use it. Let's write down that equation, that that formula, by using the three measures that we are using in this problem. So it's going to be the hypotenuse squared, so z of t, all of that squared equals to x of t, all of that squared, plus, and then the same with y of t, right? Y of t squared. Okay, that is our equation. Now we can go ahead and differentiate implicitly. So now when we do that, we need to be careful, right? Because these are functions being a square. And when you take the derivative of a function being a square, you need to use raised to any power. You need to use the general power, right? Okay, so, all right. So we are going to use that rule. Now, there's another comment that I want to make about differentiating this entire equation. So before, we have been differentiating with respect to x. right? So whenever we had implicit equations, or whenever we did before implicit differentiation, we would take the entire equation, right? So that was in my equation. Whatever I have on both sides, I would do ddx, right? I did ddx. Well, this x here meant that x is the variable. I'm taking the derivative with respect to x. Well, the variable that goes here is actually just the free variable. Before, we have been working with x as our free variable, right? Well, in this case, our free variable is t. So we are actually doing ddt, okay? So that's what I'm going to use here when I go ahead and differentiate implicitly this equation. Okay, I wanted to make that clear. Okay, so if I'm going to then do ddt of the entire thing, that is the same as doing it, on both sides, right? Well, then I'm going to just write down now, ddt applied to every single term in the equation. So ddt of z of t, then all of this squared equals to ddt of x of t, and then that squared, and then plus ddt of y of t squared. Okay. All right. Now I can go use the general power rule, right? Okay. So then, I'm going to first do the power rule, which tells me that the 2 here in the power comes multiplying in the front, right? The new power of z of t is 1. 2 minus 1, 1. But I'm not going to write power 1. And then I need to multiply by the derivative of the inside, the derivative of c of t, right? Well, the way I'm going to write that down is dz dt, all right? Because z here is like our old y in the xy implicit equations that we have seen before, okay? So, all right, so hopefully that makes sense. Well, I guess I'll explain here, like, when we were implicitly differentiating something like this, ddx, well, not xy, let's just choose y squared. We would do 2y dy dx, right? But we were doing the general power rule here, right? 2y, that's the power rule part, and then dy dx, derivative of y, right? We needed to do that. We needed to write down dy dx because y is a function of x, right? In this case over here, z is a function of t, so we do dz dt. Okay, so this z here is like the y over there. That's all. Okay, all right. So hopefully it made sense that way. Okay, so then, this thing that we did on the left side will happen again on the xt squared and the yt squared, right? So I'm just go ahead and write down 2xt and then the x dt, and then plus 2y of t dy dt. Okay. All right. Now this is now the part where I go back, look at the problem, look at the information being given in the problem, and then I plug in stuff here to find out, whatever it is that is my goal. Right. Well, in this problem, things are a bit different. Okay. Because, okay, so let's write down, let's see. So on any other problem, I will write down also another section where I do, information, and it's usually I write down here information being given, like information given in the problem, right? So sometimes you're given, like some terms in the equation, right? And well, they are given in a written way, right? They say the rate of this is that, the length of this is that, and so on, and you must interpret that as, oh, this is x of t, this is dy dt, and so on and so on. Well, you want to write that down somewhere, right? Before you go to your equation, to your differentiated equation, this one, and you plug in stuff, right? Well, it doesn't look like we have much information. But let's read again the last sentence, right? It says, find the rate at which the distance between the two cars will be changing. Okay, so that's telling us what is our goal, right? The rate of change of the distance between the two cars. The distance between the two cars here is z of t. The rate of change of that will be the derivative of that. So dz dt, right? So dz dt is what we are going after. That's our goal. Okay, right? But dz dt is just one thing. It's just one thing in our equation, right? It's just this. In order to find out what dz dt is, we need to find out what this is. We need to find out what this is, and this is, and what this is, and what that is, right? So there, like almost everything is missing, right? So what do we do then? Well, the last sentence says, find the rate at which the distance between the two cars will be changing 5 seconds later. Okay, that's the key part there, right? Because, so I'm gonna write down here, what is c of t, x of t, y of t, dx dt, and dy dt when t is equal to 5, right? Because all of these things are the things missing in the equation. But we are being told that we want to find what is this ddt when t is equal to 5. When t is equal to 5, we need to find out what is this, what is that, what is that, what is that, and so on, right? The 5 things. What are those 5 things when t is equal to 5? Well, that we can do, right? Because there's a reason why x of t was given explicitly, right? X of t was given explicitly as t squared plus t, y of t was given explicitly as t squared plus 3t. That means that you can plug in 5 there and find out what x of t is, right? So let's then go ahead and do that. So what is x of 5? X of 5 will just be, we'll just plug in 5 in here, right? T squared plus t. So that's 5 squared plus 5. That's 25 plus 5, that's 30. Then what is y of 5? Y of 5 will be, let's see, 5 squared plus 3 times 5. Okay, 5 squared is 25, 3 plus 3 times 5 is 15, 25 plus 15, that is 40. Right? Okay. Now, what is z of 5? Well, we didn't write down, the explicit definition of z of t. But we know that z of t depends on y and x of t because of that right triangle, relation that they have, right? That Pythagorean formula that we wrote down, right? So we can figure out what z of 5 will be, right? Given x of 5 and y of 5. Well, we know that the relation that is kept between z of 5 and x of 5 and y of 5 is that of the Pythagorean formula. So this square is equal to x of 5 squared plus y of 5 squared. But we know that what x of 5 is, that is 30. So 30 squared, and then y of 5 is 40 squared, and then this is z of 5 squared, right? If we want to find out what z of 5 is, then we need to take the square root of this side. 30 squared plus 40 squared. You guys must, well, some of you guys might already recognize that you should get 50 out of there, right? 30, 40, and then the third number is 50, right? The right triangle numbers. But we can check that, right? 30 squared, that's 900, right? And 40 squared, that's 1600. these two things being added, you get 2,500, right? So square root of 25, well, let me write it here. Square root of 2,500. But 2,500 is the same as 50 squared, right? So square root of 50 squared. Well, square root cancels out with the square. So then z of 5, well, and let's write it down over here. Z of 5 is 50 feet, yeah, right? Let's write down the units here, parentheses. Okay, so we have 3 of the 5 things that we need to know, right? Okay, so dx dt and dy dt are the velocities. What are the velocities when t is equal to 5? Well, that we will get by taking the derivative of each, right? X of t will be 2t plus 1, right? And when t is equal to 5, we just need to plug in 5. So you plug in 5, and what do you get? You get 2 times 5, that's 10, plus 1, that's 11, right? So the x dt when t is equal to 5 is 11. It's just the velocity of the car heading east. Now the y dt, we do the same. We just go ahead and take the derivative of y of t, and that will give us 2t plus 3. And then when t is equal to 5, we just need to plug in 5 in there. And you get 2 times 5, that's 10, 10 plus 3, that's 13. So those are our dy's dt. Okay, so the x dt is 11, and dy dt is equal to 13 when t is equal to 5. All right, so we are pretty much done figuring out, the 5 things that we needed to plug in our equation, right? So it's this, and then this, and then that, right? So we need to then come back to the equation, to the differentiated equation that we wrote over here. And we are now going to plug in our values. Okay, so 2 z of t, we found that that is 50. And then we have dz dt, which is the thing that we are going after, right? That's our goal. Okay, then 2 x of t, we found that that is 30. We found that the x dt is 11. And then plus 2 y of t, we found that that is what, y of 5, that is 40. And then the y dt, that is 13. Right? Okay. Now, since we are solving for this dt, let's see, we can already multiply this thing out. So let's see, this is 2 times 30, that's 60, 60 times 11, that's 660, right? This is that. And then this is 80 times 13. Well, 8 times 13, that's 80 plus 24. That is 112. Wait, right? No. What am I talking about? That is 104. Yes, 8 times 13, that's 104. But then there is the times 10. 1040. Yes. So we're adding those two amounts. And, we are going to divide by 100, right? So divide by 100. What do we get? 660 plus 1040, that is going to be 1700 divided by 100. That's just 17. So 17 is what we got for this dt. Okay, so we found what we wanted to find. we are not done yet though, because remember, word problem, they ask a question, you must answer the question. If you write something like that and you leave it like that, you have not finished yet your job, right? So you can write down conclusion, answer, whatever, but you need to give me a complete sentence or you state your final result. Okay. So find the rate at which the distance between the two cars will change in a 5 second later. Okay, so then this is going to be your answer. 5 seconds later, the rate at which the distance between the two cars is changing is 15 feet per second, right? And it's, of course, increasing because it's a positive amount. The distance is increasing, and it makes sense, right? Because the cars are getting farther away from the intersection, and of course, then their distance must also be increasing, right? Okay, so that's for this problem over here, problem 52. Okay, let's then go ahead and try with the second problem. All right, so this is problem 62. And this time we have a 20 feet ladder leaning against a wall beginning and it's like sliding down, right? Okay, so I drew this ladder over here and I pointed out, that it's sliding down. So the top of the ladder is going down, but it's staying on the wall and going down. And then the bottom of the ladder is doing the same, but on the ground or on the floor, right? And it's moving that way. Okay, and it says, how fast is the top of the ladder sliding down the wall at the instant of time when the bottom of the ladder is 12 feet from the wall and is sliding away from the wall at a rate of 5 feet per second? Okay, so it looks like, so the problem is about the bottom and the top of the ladder moving at the same time, right? And us finding out the stuff about the distances and how fast they are moving and so on and so on, right? So we need to, well, it is going to be useful to write down then our measures. Okay, so measures. What is the stuff that we care about in this problem? Well, we care about the position of the top of the ladder. Okay, so we are going to use a label for that. Now, the position of the top of the ladder changes with time. It means that it's going to be a function of time, right? So let's pick a letter. Well, because of the vertical position of it, let's call it y. Okay, so then the function that tells us y of t, right? Function that tells position of the top of the ladder. Okay, that's one measure that is important. Another one is going to be the position of the bottom of the ladder, right? Let's call that x of t because of its horizontal position. X of t function for position of bottom of the ladder. Okay, is there any other measure being taken into account? Well, in the previous problem, the hypotenuse was changing, right? In this one, it isn't, because the ladder doesn't change in length, right? It stays 20 feet long the whole time, right? So that's it. There's no other measure that we need to worry about. Okay, so let's see. So what we did before was, okay, so the next thing to do is going to be, writing down the equation that relates our measures. But before we do that, I want to make the following comment. So x of t is the function for the position, right? And you see that the position of the bottom of the ladder is getting farther away from this corner over here, right? I want to label or like highlight this corner over here. Okay, I'm going to call that the origin. What I want to highlight here is that the position of this one over here is, getting farther away. So, and, it's going to move at some velocity, right? Because it's getting farther away from it, the distance between it and the origin is increasing, that velocity is going to be positive, right? It's getting farther away. But I want to also say that the position of the top of the ladder, well, its distance from the origin is actually decreasing, right? Because the thing is low, is like sliding down and the top is getting closer to the origin, right? So then we are experiencing a negative change, right, as time goes on. So that means that the velocity of that, or the derivative of that, the rate of change of that will be negative. Okay, so I wanted to say that because we are going to, need that interpretation later on. Okay, all right. So as I said before, we can then go ahead and write down the equation that relates the measure. So equation that relates the measures. It's going to be, again, a, come from the Pythagorean theorem because we are looking at a right triangle. So, but what are the, the sides and the hypotenuse? Well, we chose, for here, we chose y of t, right? And for here, we chose x of t. And the hypotenuse is 20. So then the equation is 20 squared is equal to x of t squared plus y of t squared. Let me drink some water. Okay. So that is our equation. We want to go ahead and implicitly differentiate this equation. So when we do that, we are doing, again, as we did before, we did ddt of everything. So then ddt of 20 squared, ddt of, of x. No, I think it's going to be better if I do brackets of x of t squared and then plus ddt of y of t squared. Okay. Well, ddt of a constant, that's 0. For this part, again, we want to use the general power rule. And, that's going to be 2x of t. And then the derivative of x of t, which in this case is going to be the x dt, right? Following that notation that we used in the previous problem. And then the same for this other part. So 2y of t dy dt. Okay. Now we need to identify, the information that is given in the problem and what is our goal. What is it? What is the measure that, or the quantity that we want to find out? Okay, so let's read the problem again. Well, at least, the part that matters, right? How fast is the top of the ladder sliding down? Okay, for the top of the ladder, for the position of that, the function that we are using is y of t. And the question is how fast that is taking place, right? How fast that position is changing. Well, then that is the derivative of y of t. That is dy dt, right? How fast the top of the ladder sliding down. That is dy dt, right? Given that y of t is the position of that top of the ladder. Okay, so let's write down our information section. Dy dt is our goal. Okay, what other information is the problem giving us? So what is dy dt? At the instant of time when the bottom of the ladder is 12 feet from the wall. Okay, so the bottom of the ladder being away from the wall, exactly 12 feet away, that is a value for x of t, right? Because x of t tells us that distance between the bottom and the wall, right? So x of t is 12 at that instant of time that we are looking at, right? Okay, so we wrote that down, and it says when the bottom of the ladder is 12 feet from the wall and is sliding away from the wall at a rate of 5 feet per second. Okay, so sliding away from the wall at a rate of 5 feet per second. That 5 feet per second is how fast x of t is changing, right? The rate of change of x of t. That is the derivative of x of t, dx dt, right? So the x dt is 5. Okay, so that's all the information that they are giving us. Now, when we look at our differentiated equation, this equation over here, we are going after this one, dy dt, right? And so we need to know any other unknown, any other letter, any other expression there, right? So we need x of t, well, x of t we know, right? We wrote down x of t. Dx dt is 5, so we know this one over here. We still don't know y of t, right? Okay, so how do we find out y of t? Remember that we are trying to find out what dy dt at the moment in time when this is true, right? We are freezing the motion of the ladder sliding down, and we are looking at the moment in time when the position, when x of t is 12 and when dx dt is 5. Well, dx dt doesn't matter for now because, you know, we are trying to find out what y of t is. What is y of t when x of t is 12? Well, when x of t is 12, what is dy dt? You see that whichever moment in time we're looking at, the shape of the right triangle is kept. Like the triangle that we are looking at stays as a right triangle the whole time, right? So even at that moment, when x of t is 12, we still have a right triangle. Therefore, the Pythagorean equation still holds for x of t and y of t, right? So then to find out y of t, we are going to, you know, we realize that the Pythagorean equation, the relation here holds, right? So then 20 squared is equal to, well, 12 squared, right? Plus y of t squared, right? And we are solving for y of t. So then we just need to do 20 squared minus 12 squared and then take the square root of that. That is y of t. Well, I'm gonna do it step by step, right? So 20 squared, I'm going to move this 12 squared to the other side. So it goes with negative sign, right? So then I have y of t squared left on the right side. Now I'm solving for y of t to get rid of this square root of this square. We need to take a square root of both sides, right? So square root of 20 squared minus 12 squared equals to, now that I've got rid of squared, I just write down y of t. Okay, so what is this? Well, 20 squared is 400. Yep. and then 12 is 144. So 400 minus 144, that is 256. Yes, so we are doing the square root of 256. That is y of t. Well, 256 square root of that is 16. Yeah. Okay. So that is what we found for y of t. Then we have what was missing, right? So then we can come back and rewrite this equation over here, plugging in the information, the numbers that we found, that we were given in the problem, and also that we just found, right? So 0 equals to 2, x of t is 12, the x dt is 5, and then plus 2, y of t is 16, that's the number we just found, and then dy dt is what we are going after. We are solving for dy dt, then we want to send this to the other side, minus 2 times 12 times 5. You would maybe want to multiply this out. Don't do it. Okay, and don't do it. Well, I'll show you now why you don't want to do that. Okay, so then when you do that, you're left with 2 times 16 dy dt on the right side. And because we are solving for dy dt, then we need to divide by the thing multiplying dy dt, 2 times 16, right? So then minus 2, 12, 5 divided by 2 times 16. Now dy dt is by itself on the right side. Now that I have it like this on the left, I can cancel out the stuff. That is why I didn't want to multiply out, the numbers, because when they're written like this, I can more easily do the canceling. Okay, so let's see. The 2 and the 2 go away. 12 and 16, they both can be divided by 4. So I divide by 4, 12, I get 3. I divide 16 by 4, I get 4. Right? Then I have 3, 5, and 4. I cannot do any more simplifications. Now, remember that there is a negative sign there. Okay, so negative 3 times 5, that's negative 15. And then divided by 4. So negative 15 divided by 4, that's your dy dt. And remember, dy dt is the rate of change of y of t. Y of t is the top of the ladder, right? The top of the ladder is coming down. So it is experiencing a negative change, right? The distance between the top of the ladder and the origin, that's shrinking. So the change is negative. And that is reflected here with this result that we got, right? Dy dt is a negative number. Okay, so our answer is, well, they were asking how fast is the top of the ladder sliding down. The top of the ladder is sliding down at a rate of minus 15 divided by 4 feet per second. Okay, so yeah, minus 15 divided by 4, you can, get the actual decimals and all of that, but I don't care about that. I mean, and even if you don't have a calculator, then I don't expect you to write down the decimal answer. Okay, so negative 15 over 4, that's perfect. Okay, so that is this problem about the ladder. We have a third problem. So let's go ahead and do that one. And I think, yes, this will be it for this video. I will do the rest of this, in the next few days. Okay, so this is problem 64 from the practice sheet. And here we have water flows from a tank of constant cross-sectional area, 50 feet square. So this is the tank, right? And that's the water. What they mean by cross-sectional area, they mean this circle over here. Okay, so that circle over there has area 50 feet square. And so this is the tank, and the water is coming out of it through an orifice of constant cross-sectional area of 1.4 feet square. So that's the area of the circle here, the hole. That hole has area 1.4 feet square, located at the bottom of the tank. See figure. Okay, so that's what we are working with. Initially, the height of the water in the tank was 20 feet. Okay, so the height of that water in the tank is 20 feet initially. So at the beginning of time, right, when t is equal to 0. And its height t seconds later is given by this equation over here. Okay, so you would think, oh, the height is going to change with time, so h is a function of time, and you would think that, oh, maybe you should have an h of t expression, right? Like some equation, h of t equals to something that depends on t. Well, that would be an explicit writing of h of t, right? We don't have that, but what we have instead is this equation over here that relates h, the height, and also t. Now, it is valid though to still think of h as a function of t. Okay, so this h over here that you see is actually h of t. Okay, and you want to keep that in mind when you differentiate this equation implicitly. Okay, because then you will want to write dh dt. Okay, so all right, so the height of the tank and t are related by this equation over here. Okay, so, and then they ask, how fast was the height of the water decreasing when its height was 8 feet? So at the moment when the height is 8 feet, how fast is that changing? How fast is it decreasing, going down? Okay, so as we have been doing, we want to go ahead and write the measures that matter, right? So measures. The problem is about the height of the tank. So of course, h matters, right? H or h of t. This is the height of the water in the tank. Okay, so h of t is a measure that matters in this problem. What other measure matters? I don't think there is any other measure that matters, right? The radius of this cylinder doesn't change. The cross-sectional area doesn't change. We don't know anything about how much water is coming out and if that is changing or not. So although that will probably change, right? Like water flows out faster when the height of the water, it's higher, right? Because there's more pressure there, and it would come out faster. And as it goes down, water would flow out more slowly. But we're not being asked about that, right? Or yeah, so it looks like, yeah, h of t, height of the water in the tank, it's the only measure that matters here. Okay, so now the next thing is writing down the equation. Well, we are given the equation in this problem, so that is what we are going to work with. Okay, so 2 square root of h, but let's go ahead and write h of t. Plus 1/25 t minus 2 square root of 20 equals 0. Okay. What we have been doing is, once we wrote down the equation that involves our measures, we want to take implicitly differentiate it, right? So let's do that. Okay, so first of all, since we are going to differentiate this part over here, it's going to be useful to write it down as a power. Okay, so 2 and then h of t raised to 1/2, right? And then we have 1 over 25t minus 2 square root of 20. Okay, let's now do ddt of the entire equation. So ddt of 2h of t raised to 1/2, and then ddt of 1 over 25 times t minus ddt of 2 square root of 20, and then of course ddt of 0, right? Well, the constants are going to go to 0, so this is going to go to 0, and this is going to go to 0, although it already was 0. Now this is what matters, right? So this thing over here, ddt of 1 over 25t, this is a constant times t. Remember that when you have a constant times t, you can pull out the constant, and you can do ddt of t. Well, that's the same as ddx of x, right? You get 1. So then it will just be the constant outside multiplying times 1. So 1 over 25 times 1. So then this thing is just 1 over 25. Okay. We can, I will explain what happened, right? So 1 over 25 is a constant multiplying, so I can just pull it out of the derivative. And this is what I have, right? Now this is just 1, right? Okay. So then that's what we get from there. Okay, so we got 0 here, and we got 0 there, so this is equal to 0. Now we need to do this part over here. Okay, so 2 is another constant, so it will just stay there. We just worry about taking the derivative of this part over here. Okay, so this is again a function being raised to power, so we want to use the general power rule, which tells us that we have the 2 in the front multiplying, right? Well, it was already there. 1/2 will come down to the front and multiply. And then h of t will now be raised to what power? 1/2 minus 1, that's 1/2 minus 2/2, and that is minus 1/2, right? So minus 1/2. And then we need to multiply by the derivative of the inside of the function of h of t. Derivative of h of t will just be dh dt, like we have been doing before, right? Dh dt. Okay. So what now? So we have written down the differentiated version of our equation, right? And the step now will be finding out what is what we're going after, information from the problem, plug it in and see if we can solve it, right? If we can find our goal. Okay, so let's write down the information section. Information. And this is where we write down what's given in the problem, right? And also what's our goal. So the question is about how fast is the height? How fast was the height of the water decreasing? So the height of the water is given by h of t. How fast? That's the derivative, right? So the h dt is what we are going after. And what other information is given? Well, they are asking what is the h dt when the height is 8 feet. So that's h of t. H of t is 8. Okay, so when h of t is 8, what is the h of t? Well, let's look at what we got after differentiating. We have this unknown over here and this other unknown, right? The h of t, that's what we are going after. H of t, we know. And there is no other unknown, right? That means that we are ready to go and solve for the h of t. So we can then just plug in. This is going to be 8. You see that the 2 and the 1/2 cancel each other out. So I write nothing over there. The h of t is still there. I have plus 1 over 25 equals 0. I'm solving for the h of t, so I'm going to send out the 1 over 25 to the right side. It's going to go with negative sign. So negative 1 over 25. And then I have h 8, the h dt. I want to divide now by 8. Right? Oh, I'm forgetting the minus 1/2 here, right? So minus 1/2 minus 1/2. All right, so let's take care of that. 8 raised to minus 1/2, that's the same as 1 over 8 raised to the 1/2, but we know that 1/2 power is actually square root, so square root of 8, right? And 8 is, 2 times 4. You can pull out 4 out of the square root, right? Let's see. 2 times 4 square roots. You can split it. Square root of 2, square root of 4. Square root of 4 is 2. So you get that, right? So 8 raised to minus 1/2 is 1 over 2 square root of 2. Okay, so this thing over here, let's just replace it with 1 over 2 square root of 2. Okay, so minus 1 over 25. Let's see. We are solving for the HCT, and we need to get rid of this, right? We get rid of this if we multiply by 2 square root of 2, both sides. Right, and this cancels, and then the HCT is left alone, and then we have minus 2 square root of 2 divided by 25. That is our answer. I'm going to erase this. Okay, so that's what we were being asked to find for this problem, right? The HCT. You just got it. Then we write down our answer. So our answer: how fast was the height of the water decreasing when height was 8 feet? So when the height was 8 feet, it was changing, decreasing, right? Decreasing. Sorry, I'm going too fast there. Decreasing at the rate of minus 2 square root of 2 divided by 25. And what are the units here? Well, the change in the height. Well, height is feet, right? Height is given in feet. And then how fast that is going, that is changing, that's like per unit of time, right? So that's just feet per second, right? Height is just a length. So the change of a length over time, that's the unit of that length divided by the unit of time, feet per second. Okay, so that's our rate, which makes sense, right? Because as the water flows out of the tank, the height is going down. So the change is negative. So the rate of change is going to be a negative number. And what we got is a negative number. Okay, so I hope that this made sense. As you have seen already, as I am solving the problems, what I like to do is I like to organize the steps, right? I like to write down the measures that are important, that matter. And then I would like to write down the equation that relates to the measures. And then once I have written down that equation, I implicitly differentiate. And then when I look at my differentiated equation, I like to then write down the information where, I include either what I'm looking for and also the information given in the problem. And then I look back at the differentiated equation and, mark what I have, what I don't have, and what I'm going after. And then I make sure that what I don't have, I find it somehow, plug it in, and then, plug in all of those results except the goal, right? And then I just solve for that. So that is, of course, you don't have to follow what I do. Like, you're free to do whatever you want. But this is a way to keep it organized. And, it keeps everything clear, I think. right? I'm pretty sure there are other ways to also keep it clean and organized, but this is the way I have chosen to structure my solutions. Okay, so I hope that this video is, will be of help to you guys. I wish we had done more related rates problems in class. The thing is that I need, like, we need to follow a schedule of topics and, topics per day and so on and so on. So we couldn't do much of that. But with these problems, if, like, try to practice the rest of the problems in the practice sheet. And yeah, feel free to stop by office hours or to ask me questions before or after class. I will be glad to help you and answer your questions. Okay, so see you guys next time on the video about some derivatives. Okay, so the next video will be on some especially hard derivatives that I chose. All right, I'm going to stop sharing and I will pause the recording. See you guys.